In this lecture, we're going to go over the energy analysis of cycles. A thermodynamic cycle is a sequence of processes that begins and ends at the same state. So the properties at the end are the same as the beginning. So that means there is no net change of state. So we're going to look at the energy balance for cycles, and the energy balance for a system undergoing the cycle takes the form of my change in energy for the cycle is equal to my net heat for the cycle minus my net work for the cycle. Since our beginning and end state are the same, our change in energy for the cycle is equal to 0. Again, that means there's no net energy change. We can have an energy change in the processes, but for the entire cycle, there's no net energy change. So that tells us for a cycle, our net work is equal to our net heat transfer. That's actually a way you can check your problems. So there's 3 different kinds of cycles. The first cycle we're going to look at is a power cycle. Power cycles deliver a net energy transfer by work. They produce work out. So if I have some hot body and I have a cold body, I have some system. Again, the details of the system don't matter. I have some Q in, I have some Q out, and I have my work out for my cycle. So the net work of the cycle is equal to my heat in minus my heat out, where by definition Q in is from the hot body and Q out is to the cold body. In order for W cycle to be positive, Q in must be greater than Q out Otherwise, you're not going to get a positive net work out, and you do not have a power cycle. So the performance of a system undergoing a power cycle can be described in terms of the extent to which energy added by heat is converted to net work out. So our efficiency is equal to W cycle over Q in. This is our thermal efficiency. Alternatively, this is also equal to Q in minus Q out over Q in, or 1 minus Q out over Q in. And our thermal efficiency is always less than or equal to 1. only a portion of our energy added by heat can be obtained as work. So it has to be less than 1. So we're going to do a quick problem. For a power cycle operating as is shown in the picture that I drew, Q in is 17 times 10 to the 6 BTUs, and Q out is 12 times 10 to the 6 BTUs. We need to determine W cycle and our efficiency. So W cycle is equal to Q in minus Q out, which is equal to 17 times 10 to the 6 minus 12 times 10 to the 6. So our net work is 5 times 10 to the 6 BTUs. And our efficiency is going to be W cycle over Q in, which is 5 times 10 to the 6 over 17 times 10 to the 6, which is 0.294 or 29.4%. The other two types of cycles that we're going to go over are heat pump and refrigeration cycles. They're the same, it just depends on whether you care about Q out or Q in. So the goal of a refrigeration cycle is to keep the system temperature below that of the surroundings. If you think of your refrigerator or your air conditioning system in your house, you're trying to keep the inside of your refrigerator, the inside of your house, colder than the outside temperature. So in this case, if I have my hot body and I have my system and I have my cold body, we have Q out and we have Q in, and this time we have W cycle into the system. So again, Q in is heat transfer, it's into the system from the cold body, and Q out is out of the system to the hot body, and a W cycle is the net work. The energy balance in this case is W cycle is equal to Q out minus Q in. Because W cycle is always going to be negative, we just kind of reverse the equation, so we're looking more at a magnitude in this case instead of the actual signs. Just know that W cycle is negative. The performance of a refrigeration cycle is the ratio of the energy received to the system to the network. So for a refrigeration cycle, we care about Q in. It's called the coefficient of performance, or COP. In this case, it's given the symbol beta, and it's Q in over W cycle, which is Q in over Q out minus Q in, and it's going to be always greater than 1. So again, as a quick example, we have a refrigeration cycle operating as shown above. It has a coefficient of performance of beta equals 1.8. Q out for the cycle is 250 kilojoules. We need to find Q in and W cycle. So by definition, beta is equal to Q in over W cycle, which is equal to Q in over Q out minus Q in. So if I solve that for Q in, I get Q in is equal to beta. So Q in is equal to Q out times beta over 1 plus beta, which is equal to 250 kilojoules times 1.8 over 1 plus 1.8, So we get that Q in is equal to 161 kilojoules, and W cycle is equal to Q out minus Q in, which is equal to 250 minus 161, which is 89 kilojoules. So a heat pump cycle is very similar to a refrigeration cycle. It's pretty much just run in reverse. The goal of a heat pump cycle is to maintain the system at a temperature above the surroundings. So think of heating your house in the winter. I have a heat pump in my house. And again, it is schematically the same as a refrigeration cycle. We just care about Q out this time instead of Q in. So W cycle is still equal to Q out minus Q in. And this time, the efficiency, which is given the symbol gamma, is equal to Q out over W cycle, which is equal to Q out over Q out minus Q in. So if we look at an example, we have a heat pump that delivers energy by heat transfer to a dwelling at a rate of 11.7 kilowatts. The coefficient of performance is 2.8. We want to determine the power input to the cycle and then evaluate how much it's going to cost to run our heat pump for an extended period of time. So schematically, what do I mean? Here's my system. Here is Q out. Here's Q in. Here's W cycle. And here is my badly drawn house, and my coefficient of performance is 2.8. So my coefficient of performance is Q out over W cycle. It can also be on a rate basis. So W cycle is equal to Q out divided by our coefficient of performance, which is 11.7 kilowatts divided by 2.8, which gives me that W cycle is equal to 4.179 kilowatts. Our cost is our power times time times our rate. So that is my 4.179 kilowatts times 1,800 hours times 10 cents per kilowatt hour gives me a total cost of $752.22. As the last example, I'm going to look at a gas within a piston cylinder assembly. It undergoes 3 processes from state 1, undergoes a cycle of these 3 processes. We want to determine the net work for the cycle and the heat transfer for processes 1 and 2. And then we want to determine if this is a power or refrigeration cycle. Few things right here. This is actually 2 meters cubed, and V3 is 1 meter cubed. And our work is 15 kilojoules. So if we do an energy balance for each process, so let's first look at process 1 to 2. Process 1 to 2 is constant volume. So we have V1 is equal to V2. So we also know that our work from 1 to 2 is equal to 0. So for our energy balance, we're going to have delta U from 1 to 2 is equal from Q 1 to 2 minus our work 1 to 2. So our heat transfer for process 1 to 2 is equal to our change in internal energy. And the problem tells us that our change in internal energy was 400 kilojoules. Note the problem does say that we can ignore kinetic and potential energy effects. So if we now look at process 2 to 3, it's constant pressure. So our work from 2 to 3, which again is equal to the integral of P dV, it's equal to our pressure at state 2 times V3 minus V2, which is 3 bar times 1 minus 2 meters cubed. I'm going to correct my units. And I get an answer of minus 300 kilojoules. In order to calculate the heat transfer for process 2 to 3, we need to know the change in internal energy from process 2 to 3. I'm not given that, but where I can find it is I can consider my cycle. So delta U of the cycle has to equal 0. So that means that delta U from 1 to 2 plus delta U from 2 to 3 plus delta U from 3 to 1 is equal to 0. So delta U from 2 to 3 is equal minus delta U from 3 to 1 minus delta U from 1 to 2. Well, we still need delta U from 3 to 1, so if we look at process 3 to 1, we have that delta U from 3 to 1 is equal to Q from 3 to 1 minus our work from 3 to 1. Since it's adiabatic, our work is 0. So delta U from 3 to 1 is equal to minus our work, which is minus 150 kilojoules. So delta U from 2 to 3 is equal to minus 150 minus 400, which is equal to minus 250 kilojoules. So our Q from 2 to 3 is equal to delta U from 2 to 3 plus our work from 2 to 3, which is equal to minus 250 kilojoules plus minus 300 kilojoules, which is minus 550 kilojoules. So W cycle is equal to the work from 1 to 2 plus the work from 2 to 3 plus the work from 3 to 1, which is minus 300 plus 0 plus 150, which equals minus 150 kilojoules. So the net work is in. So it's a refrigeration cycle. And as a check, Q net is equal to Q1 to 2 plus Q2 to 3 plus Q3 to 1, which is equal to 400 minus 550, which is equal to minus 150. So Q net is equal to W net. So we've satisfied our cycle. That's it for this video. That also brings us to the end of chapter 2. In our next lecture, we will begin chapter 3 and examining the property tables.